Hello, today we're going to talk about optical devices. First of all, where the energy is low, the population of carrier is exponentially low. And this is the relationship among the energy and the radiation. And then if the energy is smaller than energy gap, the this material absorbs the energy. And if the energy is higher, bigger than energy gap, this material emits the energy. And this is the wavelength according to the material kind. This is the kind of material, and we can see the voltage drop according to the material. And then let's see the surface reflection. How much the energy if let's see this first. If the light go this way to such material, some of them enter into the material and some of them reflect. And how many energy go into or reflect is depend on this reflective index. And we can see reflection coefficients are this equation, and of course transmission coefficients is 1 minus reflective index. Reflection coefficient, because the total of reflection and transmission is 1. And then we code the when the moment light meet the surface, and the amount of the light transmit at that moment is FL0. And of course FL0 is equal to 1 minus R FLI. And then let's see this. Alpha means the absorption coefficients. How many lights absorbed? And if the alpha is big, the material are good at absorb, and if the alpha is small, that material is bad at absorb. And if the lights that have energy bigger than energy gap, then the carrier goes high and then dropped gradually. And if there is trap, and when the energy that is smaller than energy gap enter, then the electron placed at the trap or can go to somewhere, because the energy is small than energy gap. And if the alpha is big, it's reflected, it absorbed it well, so the slope is very high. And if alpha is small, the slope is small. And then let's see this characteristic. This black line means the direct bandgap material. The direct bandgap material has big alpha relatively than indirect bandgap material because it doesn't have the energy loss. Oppositely, indirect bandgap material have the energy loss, so it has smaller alpha relatively than direct bandgap material. And according to this process, the device layer should be thicker than alpha 1 over alpha. And then it is more efficient if the region that has electric field is bigger. So we have to give reverse bias to the material. So if the material have more light in the reverse bias region, then the more currents flow to the negative into the negative direction. So the graph go under and under, more under. So this is that graph goes under and under, and the point that graph and y-axis meet is short circuit current, and the point that the graph and the x-axis meet is open circuit voltage. And this is the equation. And in this IV characteristic, the multiply of Vm and Im is square. This square is the max that can get the power, and this blue square means the ideal max power, and we can get fill factor into this equation. And fill factor is typically on the order of 0.7. And we can get at top means power conversion efficiency into this equation. Thank you.